Problem says, which of these is true of an exponential function? This is a modeling problem just like we did with roses are red. There were a bunch of modelings that we did with linear functions. There was a mower problem that it cost a certain amount to buy the mower and then it increased by a certain amount. So we're going to go through the same steps. We're going to identify variables, x and y, and then we're going to write a function. So like an equation, f of x, that allows us to make a prediction. And then we're going to be comparing two different situations, and that's where it gets a little bit tricky. So there is a t-chart here that you need to make room for. It looks like maybe at the very tip top of the page. I'll tell you when we get there. That summarizes the two companies here, all the information. In any event, I want true, and I want everything that's true. So let's go through and see which one of these are true. Before we start, I'm going to write a data table for the zombies, because we remember zombies are exponential. So this was the day of the zombie apocalypse, and then here were the number of zombies. It went like 1, then it doubled, then times 2 again, then times 2 times 2. So the important thing that we learned with the zombies is that it was times 2 each time, which was not a constant rate. And this was y, that was the output. So we're looking for situations that look like this. So A, this is exponential, so it says in an exponential function there is a common multiplier. And that's exactly what this thing is here. I would call that a common multiplier, or the base, or the growth rates. In other words, it tells you how many more zombies you have. So there is a common multiplier to go from 2, 4, 8, 16, and that's what makes this exponential. So this is true. It has a common multiplier. As the y value, I'm reading the next one, the y value increases by some constant value, the x value is multiplied. The x value is multiplied, is that true? No, the x value is not multiplied, it's the y value that got multiplied. So this one mixed up the x's and the y's, and that makes this false. Repeated multiplication reproduces exponential data. So if you times something and then you times it again, yes, that's repeated multiplication, that's true. The graph of an exponential function is a curve, and this was in the function zoo. The exponential function curves up like this, and yeah, that's definitely a curve. This is true. And then the last one, exponential functions have a constant rate of change. No, they don't. It goes 1, 2, 4, then 8. It doesn't go 2, 4, 6, 8. It goes 2, 4, 8. So not a constant rate of change. It's a curve, and so this is false. So the ones that were true were A, C, and D. So I would leave B and E unselected here. Okay, so this one is all about the form of an exponential function, and this should be in your function zoo. Like this information is in your function zoo. It says the rule for an exponential function, I'm going to write it here. So I typed A, and I'm going to put the answer for A right here. The rule is y equals A, the coefficient, times B, the base, raised to the x power. So that's the new function for exponential rules. Letter B. Now let's identify what each one of those are. The variable A indicates the coefficients. The coefficient is where it starts. Like for example, if you start with 100 zombies, that means A is 100. So that's the coefficient where it starts. And then C, the variable A is the coefficient. The variable B is the base, otherwise known as the growth rates. Growth rates. So the B tells you how fast the zombies are growing, or how fast you're getting more carbon in the atmosphere, or more rabbits. So it's just like the slope and the intercept. You've got the coefficients and the growth rate. And then D, this is the hardest thing, because it's got this new word asymptote. All this means is, let me make an actual graph here, because this was a little confusing. Okay, so the graph of an exponential function avoids the y-axis. So it starts here, and then it increases from there. But it never does touch this line right here. So let me get a dotted line. This line right here, it just avoids the y-axis. Okay, so because the exponential function never quite gets all the way to 0, so by cutting Rice Krispie treats in half, so half, you get half, and then half of that, and half of that, and half of that, and half of that, half of that. You never actually run all the way out. It never actually touches the line y equals 0. And if a graph avoids touching a line, it's called an asymptote. All right, so the answer to what the asymptote is, y equals 0, which means that an exponential function never touches y equals 0. This is the point that I would like you to make a T-chart, and I apologize for not giving you room for it. I think you have room on the second page if you wanted to turn it over. You might also have room up at the top. But I want to summarize all the important information about these two high schools. It says, consider a change in population of two high schools, King, and Kennedy. So just like comparing Roses Are Red with Flower Power, we're comparing the two high schools, King and Kennedy. In 2005, each high school had 2,000 students. Okay, so that is the information about where they start. So that's the coefficient. So Kennedy starts with 2,000 and King starts with 2,000. So that's going to go into my function. The school district administration predicted that King High School, this one, would grow by 2%. So that's 2% for the base, which is the growth rates. Okay, so important information right there. And then the administration predicted that Kennedy's high school will decline by 3%. So decline by 3%, that means it's going down by 3%. And we're going to need to talk about what the base is going to be for those two situations. Then it says, let 0 represent the year 2005. So I'm going to highlight that. It looks like one of my variables. Okay, so 0 is the year 2005. So X here is going to be the year. Start. Let me actually, I don't have room to write out what I mean. So that's 2005 equals 0. Okay, and that's true for both of these. And I need to figure out what I'm trying to predict. Okay, so what are the independent and dependent variables? I'm trying to predict, the school administration predicted, well, what is it that's growing? We're considering a change in population. So let me highlight that. They're all over the place, the variables here. We're supposed to consider the change in population. Okay, so that's where we're predicting the output. Okay, so what we want is the population. In other words, the number of students. Okay, so I start with both schools. Both of them start with 2,000 people. Kennedy goes down by 3%. King goes up by 2%. So King is growing. Maybe these were, if this was Sunnyside and DV, which one would be King, the one that's growing? Yeah, we're growing and they're shrinking maybe. Okay, so now let's figure out the independent and dependent variables. This is independent. This is the input. And then this was the output. So let's see. X equals number of students. No, X equals years, so this is wrong. And then this one, X equals number of students each year. No, X was the number of the year. Okay, so I'm choosing between B and C. Is it the number of years since 2005? Yes. Or is it the number of years since the school has been open? No, it's the number of years since 2005. Okay, so the only one that could be correct is B. There's one other thing that did not ask, but I want to do before I move on, and that's turn these percentages into a base. So if I'm growing by 2%, that means the next year I have 102% of the students, because I had 100 to start with plus 2%. And then this one is 100 minus 3. So 100 minus 3 is 97%. Okay, so King has a 102% growth rate and Kennedy has a 97% growth rate. And that's because this is gaining and this one's losing. All right, so now let's move on to the next question. It says, we've defined the variables, now let's establish the function rule. The function rule is going to be y equals a times b raised to the x power. So let's identify what each one of those is. I know that y was the students that are in the school right now. So the current number of students in the school is equal to A is the number of students you had to start with, times B is the growth rates, raised to the years since 2005. Okay, so the function looks like this. In order to calculate the people that are at the school, that's equal to however many they started with, times the growth rate B, raised to the number of years since 2005. And I'm just going to resize this so it's a little bit better. There. Okay, so now that I've got that, I'm going to go ahead and write the function in this little column here so that I keep it organized, because there's two functions I have to compare. The first one is 2,000 to start with times a growth rate of 102%, and I've turned that into the decimal 1.02 by moving the decimal 2 places, raised to x, the number of years, so that's the function for King. And the function for Kennedy is 2,000 to start with still, but Kennedy isn't growing, Kennedy is shrinking to 97% raised to x, the number of years. So I'm comparing these two functions for King and Kennedy. Okay. All right, so it says, recall that the school district administration predicted 3% annual decline for Kennedy, and the school had 2,000 in 2005. So given the above information, okay, so let's replace each one of these quantities with what it's equal to. Okay, so for Kennedy High School, the starting students was 2,000. The growth rate for Kennedy, that's the one that was going down. The growth rate was 97%. So that's the decimal 0.97. The years since 2005 is the variable x, and the current number of students was the variable y. All right, so my final function, the current students, is 2,000 to start with times 0.97. So students is 2,000 to start with times 97% raised to x. And the one that's declining in that way, no, that's 3 to the x. That's a weird number. This one, 97%. So the correct answer is D for this function for Kennedy. I'm just going to use a calculator for this one, and the only thing that's tricky, it says, now that you have a function rule, complete the table. Remember, 0 is for 2005. Okay, so I have to replace these numbers, start with 0. 1, 2, and the reason is that it's going to be a lot easier to graph. With the year 2000, it's really hard to evaluate. And this goes up to 6, year 6, it looks like. Okay, so let's do that in a calculator. And I'm going to put both of the schools in now. So let me start by clearing my memory. All right, so the first function was for the high school we were just talking about, 2,000 to start with times 97% to the x number of years. And then the second school, I'm going to go ahead and put the other school in for y2. That's the second line I'm going to graph. 2,000 times, and this one's growing, 1.03 to the x. So this is Kennedy, the one that's shrinking, and this is King, the one that's growing. And it wants me to finish this table, so I can go seconds and table. And I wanted from year 0 up to year 6, and I want it for Kennedy High School, and that's the one that I've put in this table here. Okay, so the table looks like this. And I'm going up to year 6. The only thing that's tricky here is that it wants us to, it says round to the nearest students. So hopefully I can squeeze this in the right way. It goes 2,000 to start with, and then the next one is 1940. And now I need to start rounding, so 1882. Let me change my size here. That's a little bit better. And now I'm looking at this number here, 1825.3. 0.3 is smaller than 0.5, so I round that down. 1825. And then 0.6 I round up, 1771, 1718. This one's close. 0.5 is exactly half, and I'm rounding that one up. And 1666, because 0.9 is very close to a whole number.